Start again. We have talked about the Fourier series in the continuous time case and discrete time case beforehand. And then we will try to finish it today. So in linear time invariant system, page 14, the part 2, in linear time invariant system, signal can be represented using a set of basic signals. That's a basic concept in Fourier series. So in continuous time, we can apply if like this, we will have transform like this. If you in the major difference between continuous time and discrete time, this is for the Laplace transform or Z transform later on. We used this complex exponential. In S in here, they are complex. So in S, they can be represented as some value plus J omega, something like this. So we have used S to derive our equation to solve the problem by far. In case of continuous time, we use a symbol called Z. Z and power of M. So, N. N is N and T. We already learned that T is time, which is used for the continuous time. N is number, like 1, 2, 3, 4, 5, 6 in discrete time. So those two are corresponding. In Z in here is actually corresponding to ES, exponential. So if you see Z, that means this discrete time. Of course, we will not have a homework or anything regarding Z now. We will have a Z in later part of this lecture. Z will be given as H, also H, Z, Z, N. So if you see these two, you can see that this one is complex number corresponding to ES in here. Of course, sometimes they refer to make a symbol as S. Because it's H, while function of S squared, S plus 1, something like this, this one will be shown in the way that something like this. So that's the reason they look like in a symbol like this. So we have learned that in continuous time, we have learned that we have from minus infinity to infinite. In discrete time, we have learned that this summation, this integration will change to summation, but we should do the convolution, meaning that if you have input of this, then they will be given as a convolution of it. So this slide basically gives you an overview what will be the final thing we will see in this lecture. The final day, hopefully, in this lecture, we will understand what's the meaning of this slide. So it's too early to talk too detail about the slide right now. However, I will give you a little bit taste how you can use it. So in linear time invariant system, if you have input of X and output of Y, in chapter 2, linear time invariant system, we have learned that if input is delta, then output is H, right? H is responding to the system response of the system itself, right? So in this case, we just put this one to find the output and do the convolution to find the output. That's one thing we have done before. And we already did, in chapter 3, we have learned that this one can be represented in the way that minus infinity to infinite ak exponential minus j omega 0 kt. Right. And then this is linear time invariant system, linear system. Therefore, we have considered this one to be x is a set of addition. So it will be a set of a0, a1, exponential 1, exponential when k equals 1. So please forgive me. This is this one, but I just write down very quickly. Exponential when k equals 2, blah, 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 like this. And we can consider them, we can pass through whole signal to the system, or pass individual signal to the system, get the output, which is y. Say, this is the output of the system when we apply x. Output of the system when you apply a0, probably is this linear system, so frequency will not be changed. So this is DC, so some DC having some different amplitude will come out. And this one also, same frequency E, J, omega 0, T, and K equals 1, but different amplitude will come out. Likewise, this one, B2, E, 2, J, omega 0, T will come out likewise. So now, one way you can find out the solution is you take each component, do the convolution, and find each of it, and add eventually. Because this is linear time invariant system. As this is linear, we can separate them individually, process individually, and add them in the final value. This is what we have done before. So if you finish the calculation, you'll figure out that note that yt is given as h convolution x. Following these problems, you'll find out that this bk is actually a function of ak. So this b and this a have a relationship, which is given by, as you can see in here, h, e, j, omega 0, k, t, I think so. Yep, just omega 0. So if you remember the convolution, and also property of exponential, you'll figure out that, if you remember, I will not show the detailed derivation yet, but remember that if you have exponential j, omega 0, and some constant, and integrate them over a period, what we have learned before. When this p is not 0, of course, this one, assuming that this is integer, 1, 2, 3, 4, assuming that. In case of that, if this is not 0, if you integrate over a period, there will be 0, right? We have learned that. We have used that property a lot. If this is 0, then this one will be t, right? So if you average it over a period, there will be 1. We have learned this one. We have used this property many times. So if you see the relationship, if you put this one as input to the system and do the convolution, then convolution have this shape because there's exponential here, and the system has some component. So when you think about this, B1, only when in convolution we have say we have t and t minus tau, something like this. So using this property, you'll figure out that only this value, then it will be not 0. So when the value is k, they are not 0, that means this one will become to here, and this one come from system response of the system. Therefore, we will have this property. bk equals ak, and h, e, j, omega 0, k. So this is another way we can figure out the output. Other than doing the convolution, or other than doing the individual convolution, if you can find out what is h, Of course, note that this h is frequency component, which we have not learned yet. Of course, we learned in linear time system. Say h is frequency component. If you have small h, that's time component. Large h is frequency component. If you can find the frequency component of the system, frequency response of the system, and put them in the way, and then put corresponding k, you can find b without passing through those convolution thing. So this one we eventually will learn about. We will learn about this, and we will understand. Okay, this is why. Eventually, after passing through the Fourier transform. However, keep in mind this equation for now, because this one gives you a lot of idea how things are going. For example, if you have filter is what? Filtering is you have learned that in frequency, low pass filter is this, high pass filter is this, something like this in frequency. In this lecture, we will have plus and minus. So we will have a symmetric structure in plus and minus. Say this is omega 0, this is minus omega 0. If you see this graph, if you have low pass filter shown in this slide, this is how we can utilize this equation. So let me rewrite this equation right here. H E J omega 0 K. Note that there's no T. Let's say we already know that we have this system. We have our system is low pass filter. So this is our system. Assume that you have input and you can find output. So for example, what you can see is a circuit shown in here. So circuit shown on the graph is you have a resistor and capacitor making a low pass filtering. Say our input is E, is it J omega T? J omega T. And what is this filter? If you see this, let's write down how that looks like. The filter, whatever it is, there will be 1 when frequency is smaller or equal omega 0. There are 0 when frequency is larger than omega 0. That's how they. Let's change the omega 0 can be used in the system. So let's change the omega C. That's the band frequency. So this is how we can find out. And output will be given as H J omega, J omega here, times AK, right? There will be BK of the system. So this is our input, having just the frequency of this fundamental frequency. You got it, Christian? So when you have input, you can segmentize, you can separate into individual components. If you see this input, this is a case that k equals 1, right? So let's say if you only put this, output will come like this. And output have those relationship that in here, as these two are the same, the A1 will be 1, and BK will be A1 HJ omega, which is when AK is 1, so HJ omega will be to BK. So we already know the BK, so the output will be looks like BK times exponential and summation of it, and we only have one frequency component right here, so we will have H1 times exponential J omega T. So we already find what's Y. And what left? One left, we will find what is y. So we already find what is y. So what left is what is h in here. So you can find a relationship between input and output in this circuit. Say that this is our filter, this is our input. Let's have the relationship of it. For example, this one is R, this one is C, so corresponding inductance is what? J omega C over 1. Right? So how you can find H? How you can find H? H will be, you already know that H, J omega equals R plus J omega C over 1 over J omega C over 1. So J omega R C plus 1 over 1, that's the answer. So if you put this one to here, you will find the output. So this one is, the whole process in here is, we are assuming that the system is a linear time invariant system. If you have input, the output will come out. Those are linear relationship. We can divide, using the Fourier series, we can divide our input to different components, some of different components. Again, we can process individual components to find output. And as this is a linear system, if input has certain frequency omega, output also comes as frequency omega. There's a basic assumption in here. So say that we already know the system response, and then we have input of EJ omega in this example. Of course, it can be E2 omega. In that case, you will find A2 and B2 in this case. So if you have input of E2J omega to the system, we already know the relationship is like this. And then Y will be given as sum of BK, EJ omega T like this. However, in this case, we only have one frequency component, K equals 1. Then they will be given like this. You know that. To find H, of course, to find this one, actually we have to characterize this. We have to put the Fourier transform of this. However, another way we can find out this is using the circuit. So say that this circuit represents this. What is the output? Then you will find this multiplied by exponential, and that will solve the problem. So this one is one early age story about how to make calculations simpler using Fourier series, and a part of this is Fourier transform. However, even though we have not learned Fourier transform, we have already know the result. So using the result, what if just to use it? That's the part of this slide. So questions? All right. So let's go to the new slide, chapter 4, continuous sine Fourier transform. So in chapter 4 and chapter 5, we will talk about Fourier transform. One is continuous time, the other one is discrete time. So if you see continuous time and discrete time, what kind of image comes to you? Continuous time will be T, discrete time will be N. What kind of part of it? But what you can see in here is, in both of them, we talk about, this is first example, first equation, we will change from time domain to frequency domain, and frequency domain to time domain. In Fourier series, So this is the, I think those are those definition or some image which equation to use is very important to use this one in the future. Because if you do, I don't know what will be your major will be, whenever you will do, you will deal with the system. If you do the communication, if you do the signal processing, if you do the hardware, whatever you want to do, if you want to measure something, always signal comes in, usually analog. And how to analyze the signal? You can do the time domain analysis, or can you get the frequency domain analysis. How to change it? You have to use the Fourier transform. You have to use Laplace transform always. So I keep on saying, what's the difference when to use? Because when you want to use this, what you learned from this lecture, you have to at least know which equation to use, right? So I keep on saying this is what, this is what, this is what. For example, Fourier series, they only valid in periodic signals. If signal is not periodic, you cannot use it. So, and also, Fourier series still remains in time domain. We have a periodic signal in time domain, divide them into sine waves in time domain. So we are not using frequency domain. So if you want to use Fourier series, it should be periodic. Don't have to be sine wave. It can be a set of signal which is repeating in time. And you can divide into different signals still in time domain. That's a Fourier series. In case of Fourier transform, you can use both periodic signal and non-periodic signal. That's a strong point in Fourier transform. And we are transform means we are changing from time to frequency or frequency to time. So we are jumping back and forth between time and frequency. So that's a major difference. If you see what's the continuous time and discrete time, that comes from the calculation needs. Because continuous time is a more general form. You will see that those have something like this. From minus infinite to infinite. So from minus infinite to infinite, doing integration, it's not so bad in mathematical way, you can solve it. But in computer, if you want to do the infinite calculation, you cannot do it. Memory will burst it. So there's a reason that now, if you see the MATLAB, we don't have continuous time Fourier transform in MATLAB because computer cannot calculate. So in MATLAB, you have a command of FFT. FT is Fourier transform, while the first F is fast Fourier transform. So this equation is optimized to be processed in a computer to get a final answer quickly. So for this purpose, discrete time Fourier transform comes in for calculation limitation. So that's basically the same function, but continuous time is more general form, more intuitive way to understand. So in short, Fourier series, periodic signal, mainly time domain representation. For transform, mainly frequency domain representation, jumping over time and frequency, and then both periodic and non-periodic is possible. If we transform, I'm not meaning that it's only applied to not periodic signal. They can do both, actually. And one other thing to memorize in Fourier series is, if it's continuous time Fourier series is, signal is periodic, Fourier series coefficient is not periodic. Maybe, may not. In discrete time Fourier series, signal is periodic and coefficient is also periodic. So there's another different things. So let's have some example. Let's have an example. So let's have a periodic scale wave. We have learned this one many times. So let's have a square from t1 minus t1, they're repeating every t. And this is what? That will be given as xt equals 1 or 0, and t, how they say, smaller than t1, t larger than t1, smaller than t, there will be 0. And we already learned about that, how to calculate the Fourier series coefficient, which is basically looks like a zinc function. But zinc function is actually not exact meaning, because zinc function should have some frequency or time component. So let's say we already derived this. So let's write down. It's E sine kt divided by what? By t. K omega 0 to t1. Okay. So let's change this one to like this. So that this omega 0 t1 equals some value, and move this t to here. Move this t to here. This is t1, t. So different. So t to here, which is a period. So let's take this equals 2 sine k omega 0 t1 divided by k omega 0. That's what it say. However, let's say k omega to be omega. So it will be looks like this, and they will be looks like this. And this one is AKT. Okay? Makes sense, right? We just change the we just change define this one to be like this, and move t to this side. So we started from here. So let's see how they looks like. Before we move on, let's think about what's the meaning of this? What is the meaning of this? So let's say we have a frequency times k. What is it? What's the relationship between omega and omega 0? You can think them, omega, as harmonics of omega 0, meaning that omega is what? Omega, 2 omega, 3 omega 0, 4 omega 0, 5 omega 0, something like this. So assume that you have some kind of zinc function, let's say this function over here. Let's draw them on the frequency domain. When I once mentioned that when you draw this one in frequency domain, we'll have an envelope where we basically have a sine wave, and they decay somehow, not exponentially, but just somehow decaying as frequency goes. I already explained that that's a function. So let's say it will look like this. This is what we draw this. This is what we draw by AKT equals some function of omega. Now here's omega, not t. This is t. And we call that omega is defined to be times k. So you can think that this is original signal, This is original signal. And then for going from here to here, basically when you have this one, we are picking samples at every omega. Remember? I'm sorry, every omega 0. So omega 0 is what? This omega is what? Omega 0, 2 omega 0, 3 omega 0, 4 omega 0. So say this amount is omega 0. We are picking values at this point, and 2 omega 0, 3 omega 0, 4 omega 0, 5 omega 0, 6 omega 0. So this one is a Fourier series coefficient. We can think them as we already know its frequency component, which is given like this. And we are picking some samples in a spacing of omega 0, which is shown in here. If you see this graph, can you see this? That's how it shows. So omega 0 is what? Omega 0 is 2 pi divided by t, period, right? So as period goes larger, that means omega 0 will be smaller. So if you see this, if t is 4 times t1, t1 is fixed, so t1 is small. So in this case, it's 16 times of t, t is long. In this case, we still have same claim like that. We already know a kind of original signal in frequency domain, and picking up values in every omega 0. And when omega 0 changes by basically this, then this is what? To omega 0 is 2 pi divided by t, right? So this is 2 pi divided by 4, t1. This is the CK, the B case is 2 pi divided by 8. CK is 2 pi divided by 16. So omega 0 becomes smaller. So the logic to picking up value in every omega is still valid, but if you increase the t, you will have smaller omega 0. So spacing between the point will be smaller and smaller because you are picking more and more. So from this claim, what you can imagine is similar to what you learn from integration. In integration, you pick 2 points, calculate this area, and sum them together and make the spacing infinitely small to get the integration. It's similar to it. So the idea here is we assume that we already know the original signal. Original signal means what is the frequency component in frequency domain. How we can find the frequency domain signal? We will make those relationship omega equals omega 0 k from Fourier series we already know about, and then make those spacing infinitely small, which means make omega 0 infinitely small, so that we can have the original signal. That's one of the logic we are following. Of course, I don't think Fourier derived the equation in the way. However, if you read our textbook, the Oppenheim, one of the reasons I like our textbook. Our textbook is not so easy book. It's a difficult book. It tried to give you some idea that where this equation come from. There's always have logic, always have some reason that the equation we are using come from. So this book tried to explain as best of their knowledge. So in here, in short, we starting from Fourier series we already know about, having some assumption, and then we figure out that those function is actually sampling, picking up values in original signal, and try to find original signal. We find omega 0 infinitely small. If omega 0 will become infinitely small, that's what? omega 0 is 2 pi divided by t. Alright? So we want to minimize omega 0. How we can do it? Make t large, right? Make t large. So the logic here is if you try to find the original signal, we will try to then minimize it, and we can make the period large. So let's see how it looks like. So let's still use this. If you have infinitely long t, what happens? And this one becomes larger, the square will move, and when this one becomes infinite, they will removed from your eyesight, right? So in here, if you make this t to be infinite, then you can erase those periodic signals. So what I'm saying here is, like this graph. If you have a periodic signal having a certain signal, if you make period to be infinite, then it will look like this. There will be one-time signal, which is a periodic signal. So we can consider a periodic signal. So I like the word of non-periodic because when I speak it, it's more straightforward to listen. But actually the right English vocabulary for not periodic signal is a periodic signal, which you can see here. So if I keep on saying, okay, here is a periodic signal, and here is an periodic signal, it's sometimes confusing to listen. So I keep on using those two. So if you have a periodic signal, which can be considered to be the limit of a periodic signal as the period become arbitrarily large, meaning that the period become going to infinite. So let's assume that we have x and x tilde. In a periodic signal, x, which is in figure A, they can be considered to be when the periodic signal x tilde having infinite period. We can think in the way. So we study from the claim. So, and also please note that this x and this x tilde is equal in basic period. In this period, they are the same. Other than that, they are different. So we try to use those two claims. So x is periodic signal repeating every t, and x equals a periodic signal, which is not periodic signal. So let's have a symbol on it. In case of the x tilde, we already learned. We already learned that it can be represented in Fourier series, right? So they were given like this, and we already know what is their coefficient. So we just simply change xt. So xt is what we will try to find out. So we try just to change x to x tilde and assume that this is a periodic signal. So the first one we already learned in chapter 3. Now, let's have a look at in AK. AK is periodic coefficient, which is given as over a period x tilde t exponential minus j omega 0 kt dt. I think I'm missing something. Here one. So let's pick up the basic function. only the basic signal. So to get this one, we can pick up any arbitrary period. We can pick up from here to here, we can pick up from here to here, whatever you want to do it. So say we pick from here to here. So we are having minus t through t. Doesn't matter. In here, we claim that in here, this and this will be the same, right? So all of the logic I will show today here is we already learned Fourier series. Using Fourier series, we try to see how we can derive the equation for Fourier transform. So we try to use equation we already know about the periodic function, and then try to find equation for non-periodic function using the equation we already know about. That's all part of logic. So this is the equation. This is the equation we already learned about. But in special case, in this reason, we can change this x tilde to x because they are the same, right? So that's the reason I show in here there's x because they are the same. So in here we put xt. However, this xt is not periodic signal. This is periodic signal. So even though we change the range to infinite to infinite, because they only exist from t over 2 and t over 2. In here, there's nothing. So if you increase the period, that does not harm our claim because nothing will be added up, right? That's how we see in here. The second one. Now, we can define the envelope of TAK. TAK. Remember that in TAK, in previous case, the periodic function, they make this line. They make this line, the original signal. So let's try to find what is this one using a function of omega. So let's make it TAK, which is to simply move t to here, and that what it looks like. It's missing. I think I'm missing something. So it is a j omega 0 kt, and in here, what else we did to derive this? To find this, we used the relationship of this, right? And consider this one to be a stepping or time stepping sampling of omega when omega is infinitely long. So to get omega, function of omega, let's change this omega 0 k to omega. So to omega t. So that's what you can see in here. Now, the coefficient is what? Now, what is our coefficient? What is our coefficient? Coefficient will be t over something like this. So, that looks like that's our coefficient right now. So you can put it here. If you can put it here when you do that. So let's skip this one for a minute and go to this page. Previously in here, we can define this is a function of omega. And how we can reach the original line from the sampling, we make omega to be infinitely small. Right? T is infinitely large. So when T goes to infinitely large, T is so let's do this one first. So keep in mind about this, and then in here we can claim that like this when omega equals k omega 0. So if you recall our Fourier series, they will looks like sigma ak exponential j omega 0 k t, right? So if you put this to here, remember, now this is not x. We define a periodic signal x tilde, right? So this is x tilde. And if you put this one, let's say, let's define this one to be, how do you define it? X. This whole thing to be x j omega, because there's omega in here, not omega 0. And ak is what? Ak is 1 over t x j omega when omega equals k omega 0. That's xt, is k. So if you put in here, you can consider them as x is like this, t over 1, x j k omega 0, right? And exponential j k omega 0 t. This is what you can see in the last page. So I keep on jumping over back and forth between omega and omega 0, but the basic claim here is let's find this when omega goes to infinite. That's a basic claim in here. And we are jumping over between xt tilde and x because in one period, in the one basic period, they will be the same. We keep on using those claims. So this logic, we kind of changed to omega tilde as a function of xt. So omega tilde is the final value, but we can represent them by xt, which is not periodic signal. And then what we did is a little bit calculation. So from here, right here, let's rearrange this one a little bit. Let's rearrange this one a little bit. So how we can define it? Let's define this t. T is what? Let me change the question. Omega 0 is what? 2 pi divided by t, right? So in here we have t over 1 is 2 pi over omega 0 x j k omega 0 exponential j k omega 0 t, right? So let's move this one to the back side for a minute. That's what you can see in the third one, the last one. So now from this claim, we want to make t to infinite, meaning that omega becomes 0, so that we can match this one to be the original signal we want to find out. In that case, if the spacing goes to infinite, let's have an example. Let's say this is the graph. Let's say this is our envelope, which is the line we want to find out. And we pick up this point and this point. This point is when k omega 0 point in omega in omega domain, k omega 0, and second point, k plus 1 omega 0 point. They have a spacing of omega 0 between them. This area will be omega 0 times the amplitude of this, right? Are you following, Stopper? One more time? Yeah, okay. So, all the claim, we are assuming that we have in frequency domain, we already know the signal, and Fourier series, we are picking up point at a spacing of omega 0, as we have found out. This is the part of it. We are picking point in every omega 0, and then we're picking up kth point and k plus first point. Kth point, say point number 2, point number 3, for example, and try to find this area. This area is what? This is k omega 0, this is k plus omega 0. So this line, x length, is omega 0. Between those two. And the amplitude of this is what? This one will be x, because this one is given like this already. So there will be this amplitude multiplied by this, which is, we can see right here. So we intentionally make the form like that. So if you make omega to be infinitely small, that is the same. I once explained that it's very similar to derive the integration. This one becomes smaller because you are adding all the area. As this one becomes smaller, as omega 0 goes to infinitely small, then what? We are adding this line. We are this. This equation in here, we can consider them, we are adding those areas. However, as omega 0 goes to infinitely small, then this summation will change to integration, right? Because integration also has same claims. Integration is finding an area at each point, at each block, like this block, and this block, and this block has some area, and make those spacing to be small to find the integration, which is this line. So this one also follows the similar logic. So we figure out that those the last one, the one before the last one is same to find the block area and add them together. And then when we make omega 0 to be infinitely small, they change the summation change to integration. And this omega 0 will change to d omega. So from here to there, we'll figure out that first, this one becomes integration, and this one becomes d omega, something like this. So the final answer to this claim here is they change to integration, summation change to integration. Of course, integration will be minus infinite to infinite. We have 2 pi over 1. So this one changed to integration. We have 2 pi over 1 x j omega, because we claim that k omega 0 equals omega. But as omega becomes infinitely small, now we can change to omega. And then e j omega t, because this omega, k omega 0 changed to omega. So j omega in here, j omega t. And then finally, we will have very small omega 0, which is corresponding to omega d omega. So that will be our signal. Of course, I don't think this is I'm not sure if this is really the derivation. However, give you an idea that we're starting from a periodic signal derived our Fourier series coefficient, and then we select the period that x tilde equals x. So we are switching to x, which is not periodic signal, and then doing some calculation using this logic, omega equals k omega 0, sampling by period of omega 0. We define ak, and figure out that this tak, which makes those lines, and k omega 0, we pick a point at here, and in this line they can be represented in this way. From here we go back to our periodic signal, which is we find ak now using xt instead of x tilde t, and which is given like this. From Fourier series representation of x tilde, we already know they will look like this. We put this one to here, and then using the relationship that omega 0 becomes 0. When omega becomes 0 is what happens. We can pick a point at each point of this, and then those non-periodic signal, only the basic period left. Other one goes to infinite, and we cannot see it. So the periodic signal changed to non-periodic signal. Using this logic, we figure out that those are area in this line, and then when this omega 0 becomes infinitely small, that's similar to the integration. This one changed to integration. 2 pi stays. This one, as k omega 0 goes to infinitely small, we can change to omega. Likewise, and omega 0 is infinitely small, which is d omega. So this is the equation. So this is the equation of Fourier transform. So xt equals 1 divided by 2 pi, which come out, minus infinite to infinite, x j omega e j omega t omega d omega. This is something called reverse Fourier transform. You can change from frequency domain to time domain. You can change from frequency domain to time domain. In general, Fourier transform, it looks like this. You have, what about if you put this one e minus j omega t, then we can find this. That's Fourier transform. So those are something called Fourier transform pair. So in short, after passing through all these things, we will figure out that in non-periodic signal, xt can be represented 2 pi over 1. Let's write down x, the bottom one first. Fourier transform is given as minus infinite to infinite xt e minus j omega t dt. In case of reverse one, 2t is given by 1 by 2 pi, not t, minus infinite to infinite. This one goes to here, x j omega exponential j omega t dt. So this is the Fourier transform. So if you remember my claim, in case of Fourier series, they were given as ak is what? T over 1 over a period, x t e minus j omega 0 kt dt. In case of xt is what? This xt is of course x tilde in here. Sigma ak e j omega 0 kt, right? So I once mentioned that their polarity and many things were quite similar. So remember in this way. So xt is original signal, right? Original time domain signal. If you want to get it they usually have a plus. Both of them has plus in here. And you have learned that if you do the integration, if you make this k omega 0 to be omega, and as you make omega 0 to infinity small, this summation becomes integration. So you can think them in this way. In case of AK, which is corresponding to frequent domain signal, they both of them has minus. They have omega, omega, omega 0, and the polarity will be the same. So if you have trouble to memorize it, think that to me, I have a lot of hard time to memorize it. So what I did is, if you want to find the original signal, they usually have plus in here. Likewise, if you try to find some kind of change from original signal, you have minus in here. And relation between those two, they have k omega 0. Instead, they have omega. That's the only difference. So that's the Fourier transform. So if you want to find, we are ending the lecture now.